Hello, my name is Oleg Lesota, and on behalf of my colleagues from Johannes Kepler University Austria and Brown University USA, I'm happy to present you a modern perspective on query likelihood with deep generative models of information retrieval. Or for short, QLM goes deep, query likelihood model goes deep. So we'll talk a little bit about why generative models are interesting, what are the benefits they can bring, and how they can be implemented in a neural way. How can they take advantage of current advances of natural language processing and just deep solutions. Then we'll go to performance evaluation and see how do different generative models perform against each other and against current state-of-the-art solutions. And finally, we'll dig deeper to additional value the deep generative models bring. First of all, generative and matching. Most of currently available AI models, they follow matching paradigm with the idea that we encode a document and a query in some way. We use maybe a hard, really heavy encoding or maybe some light transformation in order to then compose them and get a relevance score. With generative paradigm, it is a bit different. Again, our final goal is, of course, the relevance score between the query and the document. But before that, we estimate the probability of a query to be generated given the document. And it is done in autoregressive manner, so word by word. For each word, we know what is the probability for this word to be generated on this position of a query given this particular document. Why is this interesting? Well, this is a fully probabilistic view to relevance estimation, which means we have a large amount of literature to back up us. We also have this granular information of which contributes to the overall relevance on the word by word level, which means we can derive some additional estimates like uncertainty estimate. And also because of this encoder-decoder architecture, we can, for example, decouple query and document encoding and keep the document encoding safe during the inference time, so making the overall system or model faster. And because of such granular approach to relevance, we can address such notions as personalization, diversity, and fairness, just because we have this access to what is under the hood of the model. The research questions of this paper. First of all, how generative retrieval models can be implemented in such a way so that they take advantage of current advances of deep architectures. How do different deep generative models perform in comparison to each other and current state of the art? What are the key features that affect performance of deep generative models? Why one kind of models is better than the other? And then what exactly is this additional value they bring? What is this mythical thing? First of all, the generative view on information retrieval, the classical one, as introduced by Ponte and Croft a while ago, is that relevance of a query to a document can be expressed as the probability for a user to use this particular query to find this particular document. This can be estimated through the probability of generating the query through the language model of the document. This is what you see above. And if we go to query likelihood model, we just apply a logarithm. We assume a query term independence from each other. And this is the formula which allows us to estimate the relevance of query to document. And usually as a model of language model of a document, we take a probability distribution of words of a document, but smoothed off on the background of the collection so that we don't have the zero probabilities there. If we take a neural spin, a deep spin on these models, we can adopt a sequence-to-sequence architecture, which consists of encoder and decoder, and it's widely used in machine translation and abstractive summarization and other NLP tasks. The idea is that first, in our case, the document gets encoded through the encoder, then the result gets passed to the decoder, which also receives the query token by token. And for each token, it can determine how probable for each word from the vocabulary is to happen and be on this position of a query. So for each query position, word position in the query, we get a probability distribution over the whole vocabulary, and from this we can compose the relevance score. And of course, because of such architecture, every probability for every word depends on not only on the document, but also on the all previously generated or situated query terms. In our work, we trained deep generative models with 3 different loss functions. One, negative log likelihood, requires only positive examples of only relevant documents. The other 2, max margin and negative log likelihood, log unlikelihood, both require negative and positive examples, meaning relevant and irrelevant documents for a given query in order to train the model. What are the models? So we adopted 4 existing well-known architectures: sequence-to-sequence, PGN, T2T, and BERT2T. And they can be easily defined or classified by what encoder and decoder are in them. So for sequence-to-sequence, it's a pretty simple architecture. We have an encoder LSTM, we have a decoder LSTM, and we use a attention mechanism over all of the encoder hidden states. So each of the words generated in the decoder attends on all the encoder states in order to produce the probability distribution of generating the next word of the query. The T-PGN, or the PGN first, is a logical step forward, quite a big step forward. It's still LSTM plus LSTM, but it also has an attention layer, but it just as well manages the out-of-vocabulary words. So if in the document there happen to be some words which are not present in the model's vocabulary, there is a probability that the model will copy it to the query in case of generation, or just recognize their importance when we do the inference with the model. So when the query is known, we still can effectively work with the words which are not in our vocabulary. The transformer to transformer is another way to elaborate on sequence to sequence. Here the LSTMs are replaced with transformers, which have self-attention, attention layers, and because of that they give better contextualization, better representations. BERT2T is one more step. It's still transformer to transformer, but it operates with word pieces instead of words, which effectively makes our vocabulary bigger. We can have the same number of word pieces as we had words, but because of different combinations of word pieces, we cover more different words overall. Finally, T-PGN is the model which we introduce here. This is basically PGN enhanced with one more layer of transformers, which gives a slightly better contextualization to the documents. Here's what it looks like. So apart from the transformer block, it is a PGN. The 2 bottom left blocks represent the encoder. So we first encode the document. We give the last hidden state of the LSTM as the first hidden state to the decoder LSTM. Then while we generate every new word of the query, the previous hidden state attends on all of the encoder LSTM hidden states. And first of all, to the right, it creates a context vector, and in combination with hidden state, it projects to the whole vocabulary and gives us a probability distribution over all the vocabulary words. And each probability means the probability of this particular word to be generated next after what's been before, the document and other tokens. But just as well, this was just sequence to sequence part. Now is the copying part. The attention can also give us the attention scores, the weighting of the tokens of the document, which can contain out of the vocabulary tokens. And from this, we can derive in the same manner a probability distribution, but over the vocabulary plus out of the vocabulary words. Combining these two distributions, we can sample from this enhanced distribution and this way be more effective and deal with out of the vocabulary words. This is the idea of PGN and T-PGN with this additional transformer layer. All right, so now we have our probability estimate for every word position in a query. What do we do with that? This information can be used, for example, to determine how certain the system is in the scores it assigns to every word and even to a per query document. So because of this structure of deep generative models, we can naturally extract the uncertainty information as the entropy over the vocabulary. So for each word position, we have a distribution over the vocabulary. We can take entropy of this distribution, and this will be our uncertainty estimate. So how uncertain the system is that the probability of this word to be generated on this position given this document is 0.2 in this example. And if we aggregate the uncertainty for all the other terms, for all the other terms of the query, we can get the uncertainty estimate for a per query document and actually try to find out how sure we are in the relevance score we give. Just as a small example, imagine we have this funny little vocabulary of 5 words and we have this query, cost for jet fuel. And there are two situations. In the first, the probability distribution is close to uniform. So pretty much there are similar chances for any word to be in this position. This denotes that the uncertainty is quite high because the entropy is high. And in the opposite case, the entropy of such distribution will be smaller, and it will mean that the estimate which the model gives to this word and to the overall query, the system is more certain in this estimate. So so it doesn't matter how big it is, the uncertainty gives additional information about how sure the model is that this score should be here. Now about the testing and experimental setup. So we test our models on MS Markov passage re-ranking collection. We test it on TREC 19 passage retrieval collection and on sparse, which is basically MS Markov dev set split into validation and test sets. For all our models, we try to provide more or less comparable conditions. So all transformer-based components were attuned to be BERT tiny-like. So 2 layers, 2 heads, and so on. When we fine-tuned the pre-trained BERT encoders, we used specifically smaller learning rate in order to not break them, to make them remain their expressiveness. And finally, for the models which required pre-trained word embeddings, we used GLOVE. Now to the performance results. At the top of the table, we have our baselines and also our state-of-the-art, such as TK and BERT. We also have 2 classical models, BM25 and QL. We have the 2 test sets, sparse, TREC 19, and 3 metrics, reciprocal rank, NDCG, and recall at 10. As you can see, each of the state-of-the-art models were trained with the recommended loss, so max margin for most of them, and cross entropy for BERT. In the lower part of the table, we have our generative models, predominantly neural generative models. Each of them was trained with 3 loss functions, and significance tests were conducted for models which were trained with the same loss function. Also, we limited this research to the neural generative models because this is our primal interest. So speaking of which, if we go the transformer way, if we try to improve sequence to sequence by adding the transformers, we see a reasonable increase in performance in the metrics and DCG, recall MRR. Sequence to sequence already outperforms the classical query likelihood, which is good news. It is also already on par with match pyramid. And by adding transformers and letting the transformers employ the word pieces, we get better performance. Interestingly, for BERT to transformer, we got the best recall on TREC 19 across all of the generative models. If we go the other way, if we go through the way of adding copying mechanism, we see that the performance increase even more, increases dramatically. So PGN and T-PGN are both already on par with conv-KNRM, but compared to the state of the art, we can see that indeed they are a bit below the TK and BERT, while still giving a decent result. So we should note that while the state-of-the-art models usually are trained specifically to estimate this relevance score, generative models do a lot of additional work. They try to understand the language, they build language models, and therefore we concentrate on the additional value they give. What else do they know? What else do they find out about the collection, the query, and the document? On a more maybe light-hearted note, we decided to make a small experiment and see what are the generated queries, what do they look like. Of course, when we do inference, we do not generate anything. The query and the document are given to us, and all we need is just to look up and multiply probabilities, and here are our estimates. But if we actually generate queries, we found some interesting things. For example, here are 3 passages to different queries, and for each passage we have generated a query in a greedy way, meaning that we always have been taking the most probable token to be the next. So for the first example, the actual query, which is relevant to the passage, is how long is life cycle of flea? The generated query from this passage is how long do fleas live? So the 2 queries are really similar to each other, even on a word-by-word basis. And this means that the model will give a high relevance score to this actual query and this passage. Below we have 2 different cases. So in the middle, the 2 queries are relevant. They make sense. They're both about the degrees which one needs to obtain to become a nurse. But the focus is a bit different, which means that this actual query will not be considered as the most relevant to this passage, but still it will have some relevance estimate. It won't be 0, definitely won't be. Finally, we have a funny example. The query is still about the flea as in the first example, but here the system got confused about what the passage is about, and therefore it asked how long do chickens live, and of course it will hurt the probability estimate, the relevance estimate as well. So just to remind you what the uncertainty is, let's have a look what uncertainty can do, how can it help us. If we take the uncertainty entropy, meaning the entropy over uncertainties of all the query words, and plot them against the relevance estimate, then we get this picture on the left. We see that as the relevance estimate decreases, the uncertainty increases, and it makes us think that there might be additional signal apart from the relevance estimate which the generative models give. And this is something we might look into on the next slide. And on the right, there's another experiment where we plotted uncertainty estimates for word positions. So for query of length 3 up to 9, the last token is of course the end of sequence token. And we can see that the uncertainty for the first token is constant and is not really varied, which means that the opening for a query is usually more or less the same. So it's a question word or one word of a fixed, small fixed set of words. We see usually some raise in uncertainty towards the middle of the sentence, because as we are done with this initial how, what words, the interesting part starts. And then again, as we approach the end of the query, the system is more sure in the score it gives. So in order to try and find confirmation of this additional signal in the uncertainty estimates, we tried to apply it to cutoff prediction. So we used a choppy, it's a transformer-based model for defining the length of the list of retrieved item, so that in order to optimize a certain metric like F1, for example, usually as an input it used the relevance estimates. And we gave it also the uncertainty estimates in addition, as additional features on a query level, of course. And we got a significant improvement in the results, which confirms our guess or our impression that indeed uncertainty estimates are valuable and they have valuable signal inside. To conclude the work, the deep generative information retrieval models, they combine benefits of classical probabilistic query likelihood models and as well with the modern neural architectures with their power. They still perform marginally lower than the current state of the art, but they improve their performance through addressing out of the vocabulary words and additional encoding capacity. They also, as we have seen just right now, can provide additional useful information for downstream tasks. For example, our uncertainty estimates for the cutoff prediction. And speaking of the outlook of what can be done next, one could develop these experiments which we've done in the collection just to use a neural generative model to better understand what queries and what documents are in the collection. And also because of this granularity, such topics as personalization and fairness can be addressed. So with this, I thank you very much for tuning in and watching until the end of the video. Thank you very much.